Now, since we've been learning about the periodic table, again, I think it's really important to understand that that word periodic means repeated in a pattern. Now, if we look at the organizations and the properties of the periodic table, we'll see that there's actually a lot of these properties that get repeated in a pattern. For example, you can see that on the left-hand side of the periodic table, our elements tend to be metals. On the right-hand side of the periodic table, our elements tend to be nonmetals. And as you move from left to right, the elements tend to become less metallic. Now, that's a pattern that we can say that exists on the periodic table. And because it's a pattern, we call that a periodic trend, something that can be repeated in that pattern, and it's a tendency of the property to change in this general direction. Now, luckily, metallic character is something that we can really see. But in chemistry, because we can't really see those little tiny atoms, we really need to talk about more invisible properties. Now, there are four that I want to talk to you about just in general today, and in subsequent units, we'll talk about these more in depth. The four invisible style of trends that I want to talk to you about are atomic size, something called electronegativity, ionization energy, and reactivity. Let's take a look at them one at a time. Size is often referred to as atomic radius, the radius of the atom, if you were thinking about it like a sphere. So if we take a look at the periodic table, we can find both the smallest and the biggest element. And there's reasons for this, and you'll have to understand those reasons later, but for right now, just know where they are. Our largest atom on the periodic table is named after a country. Francium is actually the biggest element on the periodic table. The smallest is in the complete opposite corner. The smallest element on the periodic table is fluorine. Now we can draw an arrow to connect the two. And we would call this the periodic trend for size as you go from the bottom low corner to the top high corner, the elements will tend to become smaller. And we can use this arrow to compare the relative sizes of atoms. For example, just at the top right-hand side of the periodic table, if you were comparing the size of lithium, number 3, and beryllium, number 4. Because beryllium is closer to fluorine, we would say that beryllium is smaller than lithium. Let's take a look at another trend, something called electronegativity. Now, I have heard this described as a number of ways, so we'll look at an unofficial definition and then more of an official definition. Unofficially, we kind of talk about this as the atom's ability to hold on to and attract other electrons. I've heard this kind of referred to as electron greed, although I really don't want to use those terms in class. The really official definition of this is the tendency of an atom to be able to attract electrons through a bond. So what's going to be the stronger attractor of electrons? If we take a look at the periodic table, again, we see the same two elements are highlighted. The one with the worst electronegativity, the one with the lowest electronegativity, can't really attract electrons at all, is francium, the largest, interestingly enough. And the one that can attract them the best is fluorine, also the smallest atom on the periodic table. And again, we can draw an arrow that connects the two, and we can say that in this direction, electronegativity tends to increase. And this will give you the ability of comparing two elements on the periodic table. Again, let's go back to lithium and beryllium. If I was comparing the electronegativities of lithium, number 3, and beryllium, number 4, I would say that beryllium has a higher electronegativity because it's closer to fluorine. It's more over in that rightmost direction. You could even go all the way over to halogens. Let's compare chlorine, which is directly under fluorine, versus iodine, which is 2 lower than that. You could say that Chlorine has a higher electronegativity than iodine since it is closer to fluorine. Now again, as we move forward, we'll have a reason for that. But for right now, simply identifying which one has higher or lower electronegativities will be just fine. I'd also like to talk about ionization energy. Ionization energy is the amount of energy that it takes to remove only one electron from an atom. And I don't think you're going to be surprised when you see the image that follows. On the periodic table, the same two elements are highlighted. Francium has the lowest ionization energy. In other words, it isn't very hard at all to remove an electron from it. Interestingly enough, it's also the biggest and has the lowest electronegativity. It doesn't want to hold on to its electrons, and it's easy to remove the electrons. Fluorine has the highest ionization energy. It's holding on to its electrons the tightest, has the highest electronegativity, and therefore it's the hardest to remove electrons from, has the highest ionization energy. Draw an arrow that connects it, and again you have a periodic trend. From the bottom low to the top high, the ionization energy tends to increase, and you can compare the ionization energy of elements within this scheme. Lastly, I'd like to talk about reactivity. Now, I don't really like to show this with arrows, although I'm going to, because it's not really a one-directional arrow that we're going to be using here. But reactivity in general is the ability of an element to react and form a new substance. So which ones, when you throw them together in the beaker, are just going to go crazy and react like gangbusters? On the periodic table, we tend to see the more reactive elements existing at the edges of the periodic table, and the less reactive elements tend to exist more toward the middle of the periodic table. Now, I do want to be very careful here to point out that that does not include the noble gases. The noble gases are helium, neon, argon, krypton, xenon, radon, all the way over to the right-hand side. So we're really just kind of going from the alkali metals, hydrogen, lithium, sodium, potassium, cesium, and francium, all the way over to the halogens, which starts with fluorine. They tend to be the most reactive groups. Now let's take a look at both of those groups individually. Now, in the alkali metals, the item that has the lowest reactivity tends to be at the top of the family, and the element that tends to have the highest reactivity is at the bottom. So in this group, in this family, the most reactive element would be francium. Interesting. On the flip side, I bet you can't figure out which the most reactive halogen would be. You're right, it's fluorine. Also the smallest, has the highest electronegativity, highest ionization energy. Interesting. So the most reactive element in the halogen category is the fluorine, and down at the bottom of that group is the lowest. So just one more time, if we kind of took a look at that, and we want to be a little bit careful with this trend, because again, it doesn't really flow through in a pattern. It's just these are the two extremes. The most extremely reactive elements on the periodic table are fluorine, and francium.